Chapter 6, Water Conveyance Structures. 6.1 Introduction to Power Canal. Its suitability in hydropower project. The conveyance system may consist of canal, tunnel, or pipe. 6.1.1 Power Canal. A power canal refers to a canal used for hydraulic power generation, rather than for transport. The flow of water in canal is open channel flow. Canal as conveyance system. 6.1.2 Suitability of canal and hydropower system. Canal can be a good medium of conveyance where construction of tunnel is expensive. Construction of canal is easier than tunnel. Hydropower can be merged with other purposes if the conveyance system is canal. 6.2 Hydraulic tunnels. Definition: geometrical shape, pressure and non-pressure tunnels, rock stress, hardness coefficient of rocks, hydraulic design of tunnel, velocity and sizing, introduction to tunneling methods, supports in tunnel, tunnel lining, steps of tunneling procedure. 6.2.1 Hydraulic tunnel. Tunnel is an underground passage made without removing the overburden. They are constructed for the conveyance of flow or the transportation purpose or for storage. We are here concerned with the conveyance of flow. Thus, the tunnel has been termed as hydraulic tunnel. 6.2.2 Types of tunnel. Pressure tunnel. 117. The tunnel in which flow takes place with pressure is called pressure tunnel. The head race tunnel, HRT, is pressure tunnel. Non-pressure tunnel. The tunnel in which open channel flow takes place is called non-pressure tunnel. Generally, spillway tunnel, diversion tunnel, tail race tunnel are non-pressure type. 6.2.3 Advantages and disadvantages of tunnel. Advantages of tunnel: reduces land acquisition, resettlement issue, forest clearance, etc. Environmental effect will be minimum. Natural landscape of hilly area is not disturbed. Possible shortest and direct way leads to economy. Optimum space consumption. Easy for inter-basin transfer. Time saving is shortest route to connect 2 points. Disadvantages of tunnel: normally high construction cost. Construction period is long. High construction risk. Expensive investigations. Additional cost for lighting and ventilation. 6.2.4 Size and shape of the tunnel. Size of tunnel: the minimum diameter of the tunnel is fixed with consideration of transportation, excavation, and hauling during tunneling and should be greater than 2 m for circular section, and in case of other shapes it should be greater than 1.9 m in width and 2.1 m in height. Other sizes are fixed based on the requirements. Shape of the tunnel. Generally used tunnel geometry in hydraulic design of tunnel is as follows. 118. 1. Different shapes of tunnel. Circular section. This section is most suitable from structural considerations, but it is difficult for excavation. Area, A, equals pi d4 and perimeter, P, equals 2 pi r equals pi d. D-shaped section. This section is suitable for tunnels located in good quality rocks. The main advantage of this section is the added width of the invert, which gives more working space in the tunnel during driving, and flatter invert, which helps to eliminate the tendency of wet concrete to slump and draw away from the tunnel sides. Area, A, equals 0.905 d and perimeter, P, equals 3.58 d. Horseshoe section. These sections are compromised between circular and D-shaped sections. These sections are structurally strong to withstand external rock and water pressure. They are most suitable where a moderately good rock is available. Advantages of a flatter invert are required for the construction purposes, and tunnel has to resist internal pressure. Area, A, equals 0.8293 d2 and perimeter, P, equals 3.267 d. 119. Egg-shaped section. When the tunnel is stratified, soft and very closely laminated, and where rockfall are caused due to high external pressure and tensile stress, egg-shaped section may be considered. The area, A, equals 0.864 d2 and perimeter, P, equals 3.313 d. 6.2.5 Hardness coefficient of rock. The hardness of a rock depends upon the hardness of mineral present in it. In 1822, the Austrian mineralogist Friedrich Mohs devised a scale based on one mineral's ability to scratch another. He placed 10 minerals in order from softest to hardest, giving a relative hardness value of 1 to the softest mineral, and 10 to the hardest. Each mineral in the scale scratches the one below it, the lower number, but not the one above it, a higher number. This became known as Mohs scale of hardness, and is still one of the best practical methods of estimating a mineral's hardness. Mohs hardness scale of rock. 6.2.6 Hydraulic design of the tunnel. 120. Non-pressurized tunnel design of non-pressurized tunnel is similar to design of canal. Manning's equation is the governing equation for open channel flow. Q equals 1 eta ARS. Pressurized tunnel. The design of pressure flow tunnel is computed as pipe flow and head loss is computed using Darcy's frictional factor. Discharge through the tunnel is calculated using continuity equation. Discharge, Q, equals area, A, asterisk operator velocity, V. Head loss in tunnel, H, equals FLV2GD. The permissible velocity of unlined tunnel can be 2 to 2.5 meters per second. For the concrete lined tunnel, the velocity can range up to 4 to 5 meters per second, and in steel lined tunnels, the velocity can be up to 9 meters per second. Once the permissible velocity is selected, the size of the tunnel is determined by optimization. It comprises of annual charges composed of fixed cost, cost of operation and maintenance, and value of energy losses. All the costs are expressed in terms of the diameter and should be minimum for the economical diameter. 6.2.7 Tunneling methods. There are various methods of construction of tunnels which are discussed below. Full face method. This method of tunnel construction is generally used to build shallow tunnels. In this method, a trench is cut in the soil and it is covered by some support which can be capable of bearing load on it. The cutting can be done by two methods. One is bottom-up method, in which a tunnel is excavated under the surface using ground support. Another method is top-down method, in which side support walls are constructed first by slurry walling method or contiguous board piling. Then roof is located on the top of the walls and excavation is carried out. Finally, base slab is constructed. Most of the underground metro rail stations are constructed using cut and cover method. Drill and blast method. It is the most common method of tunnel construction in Nepal. The tunnel construction is done by drilling, blasting, mucking and hauling. In drilling there are different types of cut, such as parallel cut, angle cut, etc. The steps of this method are: holes are drilled in the tunnel face. Holes are blown clean and then hand-packed with explosives. 121. Explosives are detonated. Tunnel is ventilated. Rock is scaled. Muck is removed. Support is installed. 6.2.8 Tunnel boring method. Bored tunnel method is modern technology. In this case, tunnel boring machines are used which automatically work and makes the entire tunneling process easier. It is also quicker process and good method to build tunnel in high traffic areas. Tunnels boring machines, TBMs, are available in different types suitable for different ground conditions. A special pressurized compartment is provided for TBM to work in below water table conditions. The workers should not enter that compartment except for repair works. These machines can be used in difficult conditions such as below the water table, etc. Shaft method. In this method, tunnel is constructed at greater depth from the ground surface. The shaft is built up to the depth where tunnel is required. Shaft is a permanent structure which is like well with concrete walls. At required depth, tunnels are excavated using TBMs. Shafts are provided at both inlet and outlet of tunnels. Intermediate shafts are also provided if tunnel is too long. After the construction process, these shafts can also be used for ventilation purpose as well as emergency exits. Heading and benching method. In this technique, workers dig a smaller tunnel known as a heading. Once the top heading has advanced some distance into the rock, workers begin excavating immediately below the floor of the top heading. This is a bench. Heading and benching method of tunneling. 122. 6.2.9 Supports in tunnel. The need of tunnel support arises from the fact that the excavated rock has a tendency to drop out of the roof of the tunnel. Thus, immediately after the excavation, tunnel support is done by one of the following support types. Steel ribs. Steel ribs give rigid support to the tunnel. They are made from I-beam or H-beam bent to conform to the requirement of a particular tunnel cross-section. Steel ribs support in tunnel. Rock bolts. Rock bolting is a flexible method very commonly used in tunnel. Rock bolts are frequently used as initial support at the tunnel face to obtain safe working conditions. Rock bolt support in tunnel. Timber support. Timber members are usually used in a variety of ways to provide propping or temporarily support and to provide a protective covering of the ribs. 123. Wire mesh. Heavy steel wire mesh and steel mats are used to contain the fragmented rock in the tunnel. They are pinned in the place with short, grouted steel pins or with rock bolts. Grouting. Grouting is a mixture of cement and water forced into rocks around the tunnel periphery to add strength to fractured rocks and intercept water flows. Lining of tunnel. After excavation of tunnel, lining is done to increase hydraulic capacity of the tunnel, to reduce resistance, to increase strength and to reduce losses from tunnel. Advantages of lining: provide strength and stability and facilitates tunneling in weaker strata. The hydraulic resistance of the lined tunnel is much less than that of unlined tunnel. The permissible velocity in lined tunnel is higher than that in unlined tunnel. Lining can be done simultaneously as the excavation proceeds. This minimizes the danger of accidental rock falls in the tunnel cavity and reducing the seepage losses through the tunnel. Types of lining. Shotcrete. Lining. Shotcrete is the generic name for cement, sand, and fine aggregate concrete which is applied pneumatically and compacted dynamically under high velocity. Shotcrete is used for the support of underground excavation. Shotcrete may be dry shotcrete or wet shotcrete. Plain concrete. Lining. The tunnels are lined with plain concrete when tunnel walls are to support outside pressure due to rock, but low pressure inside. Reinforced concrete. Lining. When internal pressure is high, plain concrete lining is inadequate and tension cracks are developed in lining. In such case, the tunnel can be reinforced to take up the tensile stresses. Steel lining. Steel lining is provided to provide more tensile strength to the tunnel. 124. 6.34 Bay and surge tank. Importance, location, condition of their application and hydraulic design of bore bay structure, different types of surge tank and hydraulic design of surge tank, height and cross-sectional area. 6.3.14 Bay. It is the structure located at the beginning of the penstock shaft that supplies the required flow to the turbine during startup, accommodate the rejected flow and reduce water hammer effect. Plan and section of a 4-bay. Functions of 4-bay. The various functions of 4-bay are enlisted below, to allow for the transition from open channel flow to pressure flow conditions. To regulate the flow into the penstock, particularly through the release of excess water into a spillway. To release surge pressure as the wave travels out of the penstock pipe. To serve as secondary settling basin. To provide water storage for use during peak power demand if necessary. Components of 4-bay. The various components of 4-bay are entrance bay or basin, spillway, trash rack or fine screen, flushing sluice valve or gate chamber, penstock pipe. Design considerations of 4-bay. The velocity of flow in 4-bay is assumed to be in the range of 0.1 to 0.2 m/s. 125. To avoid air entrainment at inlet or minimize vortex formation, minimum submergence, S, is provided. Maximum of the value given by the following three formulae: S greater than or equal to 1.5 d, S greater than or equal to 1.5 v2 g, S greater than or equal to 0.54 vd. Here, Vp equals velocity in penstock, dp equals diameter of penstock. Maximum drawdown of water in 4-bay, Z, is given by Z equals VALAG. Here, LP equals length of penstock, AP equals area of penstock, AF equals area of 4-bay equals LXB. Vp equals velocity in penstock. Effective depth of 4-bay, H, equals diameter of penstock, dp, plus minimum submergence, S, plus maximum drawdown, Z. Overall depth of 4-bay, HO, equals effective depth, H, plus settling depth, 0.5 m1m, plus freeboard, 0.5 m1m. Length of the spillway provided to safely overflow. Design discharge is given by L equals QCH. Here, CD equals coefficient of discharge, general value 1.6 to 2.2, depending upon the shape of the crest. H equals head over the crest, 0.5 to 1, M storage volume equals discharge, Q, asterisk detention time, T. Design steps of 4-bay. Calculate submergence from given three formulae. Adopt maximum of those values as minimum submergence, S greater than or equal to 1.5 d. 126. S greater than or equal to 1.5 V2 G. S greater than or equal to 0.54 VD. Calculate maximum drawdown, Z. Z equals VALAG. A. Assume effective depth of 4 bay, H. Calculate plan area of 4 bay in terms of H equating volume, QXT equals AH. B. A equals QTH. C. The effective depth of 4 bay is given by H equals D plus S plus Z using equation A, B, and C. Solve for H. Assume mean velocity of flow in the 4 bay, V, in the range of 0.1 to 0.2 m/s. Using velocity assumed above, calculate width using formula B equals QVH. Adopt suitable value of B. If B is changed, check for the velocity in the 4 bay. V equals QBH. Calculate the length of the 4 bay, L equals volume, QXT, BXH. Calculate the length of the spillway, L equals Q. CH. Required length of the spillway should be less than the adopted length of the 4 bay. Calculate the overall depth of the 4 bay after assuming suitable value of settling depth and freeboard. H0 equals H plus settling depth plus freeboard. Hence, the size of the settling basin is adopted as L** operator BAD opt * operator Ho. Draw the figure of the 4 bay and mention the design dimensions. 127. 6.3.2 Surge tank. Surge tank is a large cylindrical tank provided near the downstream end of the penstock to relieve excess pressure caused by sudden closure of the valve. The surge tank is located between the almost horizontal or slightly inclined pressure conduit and the steeply sloping penstock, respectively pressure shaft, and is designed either as a chamber excavated in the mountain or as a tower rising high above the surrounding terrain. Functions of surge tank: provide a supply of water when the valve is suddenly opened to reduce the water hammer pressure at store water at the line of load rejection until the penstock velocity has been decelerated to the new steady state valve. Types of surge tank. According to the hydraulic design, they can be classified into the following classes. Simple surge tanks. It is unrestricted tank of constant cross-sectional area in which the maximum variation of water level is contained within the tank. This is very sluggish, moving or reaching more slowly than normal, in action, and costly since it requires greatest volume. Simple surge tank. 128. Restricted orifice or throttled surge tanks. It decreases the amplitude of the surge and effects more rapid reduction of the mass oscillation and thus gives an economy up to 40% compared with the simple tanks. But the disadvantage is that it allows part of the water hammer pressures into the conduit system. Throttled restricted orifice differential. Differential surge tanks. Differential tank separates out the two functions of simple storing of additional water and effective accelerating and decelerating of water in the main conduit by the outside main tank and central river respectively. Thus this type has got the combined advantage of a simple and restricted orifice type surge tanks. 6.3.3 Design of mass oscillation in surge tank. Let us consider an arrangement as shown in figure. V is the velocity of water in tunnel. Let AD is the area of tunnel. QT is the discharge through the tunnel. The discharge through the penstock is QP. Using momentum equation 1 and 2, pH asterisk at plus rho gz at pi asterisk at equals m asterisk, assuming pi equals pH, neglecting friction, rho gz at equals m asterisk rho gz at equals at asterisk L asterisk rho asterisk dv dt equals minus GLZ. 129. Where VE sign indicates retardation. Using continuity equation at section 2. QT equals QST plus QP equals plus for sudden closure of valve, QP equals 0 equals at equals AST. We have VST equals thus, the continuity equation becomes plus Z equals 0. Solving above differential equation, we get Z equals asterisk sin T HG equals gross head The minimum area to be provided for surge tank is calculated using TOMA formula, and hence factor of safety regarding area of surge tank is calculated as factor of safety equals so, height of surge tank is given by H equals up is down plus HF plus freeboard, 2m. 6.4 Penstock and pressure shaft, importance, location, condition of their application, water hammer pressure computation by RWCT and EWCT, wall thickness of penstock/pressure shaft, steel, economic diameter of penstock, optimization study in brief. 6.4.1 Penstock is a pipe that conveys the flow from the forebay or surge tank to the turbine. Water hammer. When the velocity of liquid is abruptly decreased, the momentum of the liquid will be destroyed and consequently a high-pressure wave is set up. This wave of high pressure will be transmitted along the pipe and may create a knocking noise and vibration in the pipe. This phenomenon of sudden rise in pressure in the pipe is known as water hammer. Causes of water hammer. Following are the causes of water hammer: valve operation, power failures, starting or shutdown of pumps, fluctuation in powers. 131. Rupture of the line, mechanical failure of control devices. Effect of water hammer: high pressure fluctuation in pipelines. Rupture of pipe or valve if beyond safety limit. Higher pressure requirements for the design of pipelines and penstocks. Water hammer pressure computation. Let T be the time of closure of valve. To study the pressure change with time at a point in the pipeline, the valve closure time can be classified as instantaneous closure, T equals 0, rapid closure, T equals 2L/C, gradual closure, T2L/C. (133) Hoop stress, sigma, equals PD2T. Since hoop stress is greater than longitudinal stress, hoop stress is used for design of penstock pipe. So, thickness of penstock is given by T equals PD2 sigma, where sigma A equals allowable stress in penstock pipe. Considering joint efficiency, thickness is modified as T equals. In general case, the thickness of penstock is calculated by formula of ASME, T equals PR sigma beta minus 0.6 P plus 0.15, corrosion allowance, cm. Here, T equals thickness of penstock and cm. P equals total pressure in penstock pipe in kg/cm2, or equals radius of penstock pipe in cm. Sigma A equals allowable stress in kg/cm2. Eta equals joint efficiency. 6.4.2 Economic diameter of penstock pipe. With the increase in the diameter of the penstock, the head loss decreases as given by Darcy's formula, and hence the revenue loss decreases. At the same time, with the increase in the diameter of the penstock, the cost of the pipe increases. Thus, the diameter of the penstock pipe that optimizes these two costs is called economic diameter of penstock. Methods of determination of economical penstock diameter by using empirical formulae. USBR formula, V equals 0.1252 GH. Economical diameter D equals Sarkaria formula, D equals 0.62 ... Design guideline by JNN, D equals dot. Here, H equals head in mHd equals dynamic head in MP equals power in HP, 1 HP equals 746 watts. 134. Analytical method. In this method, the annual cost of the pipe and the annual revenue loss are analytically calculated in terms of diameter of penstock. The total cost is differentiated with respect to diameter and equated to 0 to get the economic diameter of penstock pipe. Head loss through penstock pipe, H equals power loss due to head losses, P equals eta gamma Q. H equals eta gamma Q equals energy loss, E equals PXT equals TLET, R is rate of energy, then, revenue loss in energy is, C equals XR. i.e. C equals 8 eta gamma FLQ. Pi GT R1D equals a D, where A equals TR. Now, the thickness of penstock by hoop stress formula, T equals volume of penstock material, V equals pi dl. T equals pi dl equals D. Let RP is rate of penstock per unit volume. Then, cost of penstock is C equals VXR equals D. Let CRF is capital recovery factor, then the cost of penstock is converted into annual as C equals CXCRF. Here, CRF equals, hence, annual cost of penstock, C equals pi LPR2 sigma CRF D equals BD. where B equals CRF total cost, T equals S plus CAT equals a D plus BD. For minimum cost, first derivative is equal to 0, i.e., dT/dd equals 0. dD/dAd plus BD equals 0. i.e., minus 5AD plus 2BD equals 0. Minus 5AD equals 2BD. D equals 5A2B. 135. D equals 5A2B. This is an equation to determine the economic diameter of penstock. Graphical method to determine the optimum size of the penstock pipe by the graphical solutions is as follows. As we know that frictional head loss will increase with the increase of the velocity of flow and decrease of the diameter of the penstock. The increase of the frictional head loss is the loss of the useful head for the generation of the electricity. The practice for decreasing the head loss is to use the bigger diameter penstock pipe with together decreasing the velocity inside it. But the increase of the size of the penstock will cause the increase in the expense of the material due to the increase in volume. So the selection of the diameter of the pipe should be done through the hydraulic analysis with considering the energy loss due to the head loss. For this analysis, several diameters of the pipes are selected and its cost in terms of annual expenditure is calculated. Consequently, the annual energy loss cost is also calculated for these diameters. Both of these costs are added and minimum of it corresponds to the economical diameter of the penstock. 6.4.3 Head loss calculation in conveyance system. Head loss in conveyance system can be categorized into two major categories. Major head loss. The major head loss in the conveyance system is the friction loss in length. For open flow conveyance system, H equals V eta LR. 136. Here, V equals velocity of water, N equals Manning's roughness coefficient equals 0.012 to 0.018 for concrete line tunnel, L equals length of conveyance system or equals hydraulic radius for pipe flow conveyance system, HF equals where V equals velocity of flow, L equals length of the tunnel, D equals diameter of tunnel, F equals Darcy's friction factor. Minor head loss. The minor losses include trach rack loss, entrance loss and transition loss, bend loss, gate loss and exit loss. Trask rack loss, H equals where KT equals loss coefficient equals 1.45 minus 0.45 or minus or 2 or equals ratio of net area to gross area. V equals velocity of flow through trash rack. Entrance loss, H equals where Q equals loss coefficient for entrance, V equals velocity of flow. Transition loss. The transition loss may be due to expansion or due to contraction. H equals K, V minus V, 2G. H equals K, V minus V, 2G where K equals loss coefficient for expanding transition, KTC equals loss coefficient for contracting transition, V1 equals velocity of flow at the beginning of transition, V2 equals velocity of flow at the end of transition. 137. Bend loss. H equals KV2G where KB equals bend loss coefficient, depends upon relative roughness and ratio of diameter of tunnel and radius of bend. V equals velocity of flow. Exit loss. H equals KV2G where Q equals loss coefficient for exit, taken as unity, V equals velocity of flow. 138.